Hello, this is Ryan Winterhalter doing my Skill 18 Honors Pre-Calculus Checkpoint video. My phone's running a little low on storage, so we're going to try to make these videos a little bit faster. So here we go. Now, the problem here is create an arithmetic sequence, write an expression for the sum of the first n terms, and then prove that you are correct using mathematical induction. Okay, let's get right into this here. So we chose our arithmetic sequence. It is 1, 3, 5, 7, 9, all the way until term n, whatever. And so right here, our starting term is 1, and the term number is n, and the rate of growth is 2. We're adding 2 every single time, right? So we can simplify this if we want to, and go from 1 plus 2 times n minus 1 to an equals 2n minus 1. Now we have to find the sum of an arithmetic sequence. Now we know that if we imagine that we flip these numbers around, instead of doing 1, 3, 5, 7, 9, we do 9, 7, 5, 3, 1, that they will all add, and we add the two together, we will get the same for every single addition. So we will get, because 9 plus 1 is 10, 3 plus 7 is 10, 5 plus 5 is 10. And this works for almost any term. If we extend it out to 11, 1 plus 11 is 12, 3 plus 9 is 12, and 5 plus 7 is also 12. And so if we flip those and add them together, we will get the same number here. That's where the A1 plus AK comes in. And we multiply that by the total number of terms that we're going out, because remember, it's the same for every single one. And then we divide by 2 because we added the 2 together, but we only want the sum of just 1. Now, from here, next we need to prove that the sequence works for one variable of n. And we can choose 1 to make the process simplify by finding the sum of the first term, which is simply 1. Now, we did this by setting up our problem, right here like this. And we could prove it using 5, we could prove it using 1, we could prove it using any number. But right here I chose 5, and so what I did was I just had to make sure, using this information here and plugging in the corresponding stuff here, I'll show you how I simplified this here. So what we did was we took our sum here and we plugged in what we knew. We knew A1 is equal to 1, so we plugged in 1 for that. And we know that AK, or AN, is equal to 2n minus 1. That is, so the current term plus the starting term, current term equals this, as we simplify it up here, and this is our starting term. Now we can plug those in and we can simplify it out. Basically what we do is when we add these together, we get 2n times n, so 2n squared over 2, which simplifies to just n squared. So this statement here is true. Now we just have to prove with one variable, so 5, for example, plug it in, it works, okay? We can prove it for 1 to get a sum of 1. But we just have to prove that for one number it works. And we can plug that in to this over here. We can plug it in here and plug an n, and then 1, and 1 for these 3 n's, and then solve for that. Either way, we will get the exact same thing. So now, because we're able to plug in n squared for this, because they're equal, what we can do is actually, so after we simplify our sigma notation, it tells us that the sum of the first term is 1. Now we just need to prove using induction that this works for both n and n plus 1, but we have to add the next term value to the n, because then that would make sense, right? If we're having the sum of the first 5, then we go over to n plus 1, so the first 6, well, to that 5, we're going to have to add the 6th term. So what we can do is we can set it up like this. We can add sigma of k, ak, n plus 1. Over here, we just have the n, but we add on that next term, right? We have to add in the next term, and that is just 2n plus 1. So basically, what we end up doing here is we end up, the next term that we add would be 2n plus 1 minus 1. And let me think about it. The reason for this real quick is because if you think about it, go up here to our simplified problem, right? This is for term n, but we need it for term n plus 1. So this is the exact same as this, but we just plug in n plus 1 for n. And so then we can simplify that to 2n plus 1. Now, what we have to do is we can substitute in n squared for this value here. Now, down here, so we substitute in n squared and we simplify that to 2n plus 1. This simplifies to n squared plus 2n plus 1. So now now going over here and doing n plus 1, we just have to prove that this will end up equaling this. Because if it does, then this proves, using mathematical induction, that for every single term in our sequence, if we add them up together, that this statement is true. That if it works for 1, then it works for 2. If it works for 2, then it works for 3. And it's like a domino effect. Basically, we have to prove for 1, and then prove using mathematical induction that it works for everything plus 1 to that. And then so basically, we can start at the simplest one and go from 1, and if it works for n plus 1, or if it works for 2, then we're good to move on for 3 and 4 and 5 and so on and so on. So basically, what we can do here is we know that this is true, right? Well, now if we change n to n plus 1, then we have to change this over here to n plus 1 as well, right? So this, if we made this n plus 1 like we did down here, we could substitute in for this n plus 1 in parentheses squared, right? Which is what we did here. Because if you think about it, if you're changing, these are the exact same thing. This n equals this n. Now, if we just change this n to n plus 1 and this n to n plus 1, it still stays equal. You're not doing anything illegal, so to speak, when you're substituting in the n plus 1 for both of them. So when we plug that in down here and we FOIL it out, it does turn out that n squared plus 2n plus 1 equals n squared plus 2n plus 1, which, as I said before, proves to us that when we have the sum of a certain number plus the next term to that series, so we have the series of a certain sequence here, right, to a certain number of terms, plus the next term in that sequence added on equals the series of that sequence just one farther than this, right? This is taking this one step farther, so these should conceptually make sense, and from down here, as we can see, they mathematically make sense, which is why using mathematical induction, we are able to prove that for this sequence, indeed, this statement is true, and this statement down here is true, and that this sum sequence will work for every single term value, be it 1, 5, 10, 100, 1000, you name it. It should work, because we proved with mathematical induction, it should work for every single term in the sequence.